Hello, welcome to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. My name is Farid Char, and with the producer, Hector Salas, we are going to be your guides during this trip, this virtual visit to ESO Paranal Observatory. Just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I have been working for Paranal Observatory for more than 10 years, and I am also part of an astronomy center in university in Antofagasta. And regarding my personal hobbies, I am very interested in astrophotography. So if you want to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So as I told you before, I am not alone. I am here with Hector. So he will act as the producer for this streaming. So hello, Hector. How are you?
Hi, Farid. I'm fine. Happy to be here again. So, I'm a PhD student at the Leibniz Institute in Astrophysics in Germany. I work mostly with topics related with the circumgalactic medium, that is the environment that surrounds galaxies. And I have been a member of the team of guides from Paranal Observatory since 2019, while I was doing my master's in Antofagasta. And as Farid said, I'm going to be the producer today. So that means that I'm going to be changing the videos, but also be reading your comments. And if you have any question, I will try to look for the answers for them. So if you have any comment, any questions, any salutes, everything, you can just post them in Facebook or YouTube, and we'll have a space during the tour to answer all your questions. And yeah, okay, I guess we are
Okay.
ready to start.
Yeah, thank you very much, Hector. So please remember, you can send your questions or comments during all this streaming. I can imagine you already have some questions. So to do that, you can leave your questions or comments in Facebook or YouTube, and you can say your name or and city, and we are going to announce and share this with everyone. So Hector will be waiting for your questions to answer them later during this tour. Okay. Okay, so we are going to start with this virtual tour. And the first thing I want to do is to help you to understand the place of our visit. So we will begin this virtual trip with some information about the European Southern Observatory, or ESO. So in this case, ESO is composed of 16 member states, as you can see in this screen right here. So the headquarters of ESO are located in Germany. Okay? And also Australia has recently joined ESO as a strategic partner. So Chile is the host state and is the home of all ESO observatories. So from the 60s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations. I mean, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories, such as ESO, to our country. So as a result, Chile offered its territory and ESO did choose the more suitable areas. So the mission of ESO is to design, build, and operate astronomical observatories. And why? Well, to enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. So right now, you will see a picture with the three observation sites of ESO in Chile. Okay, here we are. So in first place, we have the Chacnantor Plateau. This is the site of the ALMA and APEX radio telescopes. ESO is part of these places for radio astronomy, alongside other international partners. Additionally, south of the Atacama Desert, at 2,400 meters above sea level, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT or the 3.6 meter ESO telescope. And this one specifically is using the HARPS instrument. and this one is an exoplanet hunter. Finally, we have the place of our visit, the Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT, the most advanced visible light telescope on Earth. So in the next few years, we will also have the Extremely Large Telescope, or ELT, and this will be the biggest visible light telescope on Earth. Also, the CTA will be an array of telescopes, in this case with a focus on capturing gamma rays. Okay. Well, now we have a better picture. So now let's travel to the Paranal Observatory. We are going to do a virtual visit. Okay. So as you can see, we are doing a virtual trip to Paranal. So we are flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital Santiago. Specifically, about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we are going toward the mountain top of Cerro Paranal, located at 2,600 meters above sea level. This mountain belongs to the coastal range, and despite its altitude, it is located at just 12 kilometers from the coast. And where's the ocean? Well, the Pacific Ocean is located just below of the cloud cover, as you can see in this picture. And why those clouds? If right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt current. This is a cold current near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy. And about the layer, instead, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. And the clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. Now, what other natural barriers we have in this area? Well, about 200 kilometers to the east, we have the Andes Mountains with very high mountains, in this case, more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds from Argentina and Bolivia. So the main result is this landscape, a place with an average of more than 300 clear nights per year, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity. I mean, light pollution. So this is one of the best places on Earth for astronomical observations. Okay. So right now we will change the view to have an even closer look to Paranal. Okay, here we are. So as you can see, this is not an ordinary mountain. And now we can see the different telescopes and structures in the mountain. We are at the summit of Cerro Paranal. Do you know what Paranal means? Well, in the Quechua language, Paranal means whirlwind, possible, possible, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere here is extremely quiet. This observatory is a true oasis. So you will see how in one of the driest deserts, we have a lot of life and a lot of science. Okay, so right now we are going to visit the summit of Cerro Paranal. Okay, so here we are. So in front of us, we have the Very Large Telescope, or VLT, its acronym. So if you see the amount of buildings, I mean 4 giant domes and other 4 small and rounded ones, it is clear that very large telescope, in fact, is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. Okay, so let's take a closer look. So here you can find the 4 unit telescopes or UTs, each one with a primary mirror of 8.2 meters of diameter. I mean the giant ones here, okay? And the other small ones, like this one, are the auxiliary telescopes or ATs, each one with a primary mirror of 1.8 meters in diameter. Okay, so we have one here, we have another one, we have another one, and we have this last one. Okay? So each UT has a name in Mapudungun language. This is the language of the Mapuche people, natives from central south of Chile. So in first place we have here Antu, and Antu means sun. Here we have Cuyen, and Cuyen means moon. Here we have Melipal, and Melipal means 4 stars, but this is a reference to the Southern Cross constellation. And here we have Jepun, and Jepun is a word associated with Venus because this word Jepun is a concept that is talking about like the evening star. Okay, so in this case, this is the information regarding the UTs, and as I told you already, the small ones here are the auxiliary telescopes. The auxiliary telescopes are mobile and they can be moved in this platform using a rail system. So we can move them up to 30 different positions. They were specifically designed to work all together, okay, as a single big telescope with a variable diameter, able to reach up to 200 meters, as you will see in a few moments in a simulation. Here we have the simulation. So this technique to combine light from several telescopes is called interferometry. So we are able to observe much more specific details if you compare this with the individual telescopes. So thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. Okay, so right now we will come back to the tour screen. Okay, so now you will have the opportunity to visit one of the telescopes. Um, we are going to visit this one. We are going to visit the UT3 or Melipal. We can't enter all the telescopes, but don't worry about that because the 4 ones are identical in size and shape. So the only difference are the instruments inside. So you can learn more about the instruments on the ESO website. Okay. So now we are going to enter to this one. We are going to enter to UT3. Okay, here we are. So now we are on the Melipal telescopes, and what can you see? Well, this is a giant telescope. Okay, you can see it's a very big telescope. You can see some people here, so you can have an idea of how big is this machine, this big machine. Um, and as I told you already, we have a big mirror inside of 8.2 meters in diameter. So in this picture, we are on the last floor of the telescope at the same height of the main mirror there, okay, in front of us. So I am going to do a close-up so you can take a better look to this mirror. So the mirror here has 22 tons with 8.2 meters of diameter and only 17 centimeters thick. And the mirror was created from a ceramic and flexible material called cerudur. So how can we point to the sky with this telescope without breaking it? Well, we have to take a look at this telescope from another angle to understand better what happens. Okay, so I am going to change the view and I will show you the telescope from this different perspective. Okay, so in this new picture, in this new view, we are in something like the platform, just at the one floor, let's say below of the previous picture. So from this perspective, you can see that the mirror is mounted over this white structure. You see, this is a cell supporting all systems assisting the mirror, including something called active optics. Okay, so and here you can see some little gray boxes. I will make close up. I mean this. Okay, these boxes here, these little boxes, are something called actuators. So the actuators are a kind of piston, and we have 150 in total, and they are all controlled by computers. So they are acting on the mirror during the observations in order to keep the optimal shape of the concave mirror, because the main mirror, the primary mirror, is concave. Otherwise, it could suffer deformations just because of gravity or physics. So those deformations are imperceptible in a first view, but they could be critical in the result of the observations. So how is this working together? We will come back to explain that. So we are going to change the view one more time to explain what happens when the telescope is observing at night. So in order to explain this, we have a short animation. We will take a look in a few moments. Okay, here we have the animation. So you can see that the first step is to open the dome. Okay, of course this is an exaggerated view when we have to open the dome. So basically the telescope will receive light, and in first place the light will be received by the primary mirror, then will be reflected to the secondary mirror in the top, and then will be reflected to another mirror in the middle, so we can transfer the light to one of the instruments. And also we can let the light go pass through the a centerpiece in the middle. So basically we have three different instruments. In this case, those boxes in red, blue, and green. So basically we have three possibilities. We have three possible instruments to receive the light and to convert this light into a digital picture. So basically, the instruments are something very, very complex. For example, this is one of the instruments, and you can see that in this case, the people here, they are working to prepare the telescope for the next observation night, and also, if necessary, to fix or calibrate or do any work in the instruments here. So basically, this is one of the instruments, but we have another one in the opposite side, and we have another one in the base. Okay, so we have three possible instruments if we want to use any of the instruments with this telescope. Okay, so basically this is what happens here. This is what happens in the telescope. During the day, um, we have only the engineers working, as I told you already, in order to prepare the telescope, to fix any problem, this kind of stuff. During the night, the people is not here. We have the astronomers in another location, and we are going to visit in this virtual tour this additional location. So, but this is what happens here in the telescope at night. So now we have to go outside because we are almost ready here, and we have to move to the other location. We have to move to the control room. Okay, so I am going to go out. I'm going to return to the platform view. And the next stop will be the control building. The control building is this building here. As you can see, it's located in the same mountaintop, but not in the same level of the telescopes. So it's in a different level. So in a few moments, we are going to visit this place because this is the place where the science is happening at night. But before going to this place, the control building, um, I would like to know if maybe we have some questions or comments from our virtual visitors. Hector?
We don't have any questions so far, but we have several greetings. So we have Kapitu from Singapore, telling us that astronomy is his life and his dream. We also have Massimo from Italy. We also have a couple of our regular viewers, Jose Maria, who almost always joins in these tours, and Sue Graydon from Amsterdam as well, and some greetings from Chile, from Ismael, and from Toronto we have Tuba. But so far, no questions. So let me ask you one of the usual questions that people ask in the in-person tours. Uh, what kind of maintenance is needed to be done to the telescope, to the mirrors? Do you need to clean them, do something with them? Can you tell us about that?
Yeah, sure. Let me come back shortly to the telescope to explain this. In this case, the mirror is the most delicate part of this telescope. And yeah, we need to do some maintenance to keep the mirror in optimal conditions because Paranal has more than 20 years of operations. We are using the original mirrors. So basically, we have two ways to clean the mirror. One way is, let's say, an easy way, and we need to do this once a month. And for this, let's say, easy maintenance, we need to rotate the mirror a little bit, and maybe a couple of engineers will spread a carbon dioxide snow on the mirror. So this is something like a foam, and this element will remove dust from the mirror because we are in the desert and we have dust. So basically, we have to remove this dust in order to keep the mirror clean. But this is something like a not so complex maintenance, and you need to do that only once a month. But the other maintenance is a bit more complex. We need to do another maintenance every 2 years. And for this maintenance, we need to remove the entire mirror from the telescope. I mean, we need to remove this mirror, okay? But also we have to remove the white cell. We need to remove all of this. We need to remove the mirror and the white cell. We need to do that using some special cranes. So the cranes will extract the mirror to the outside, and in the outside we have a special vehicle, and this vehicle will take the mirror and will transfer the mirror down to the base camp. So in the base camp, we have a special facility. It's the mirror maintenance building. So in this special building, the mirror will go through a process that we call recoating, because the mirror, by the way, the surface of this mirror is made from a very thin layer of aluminum. Okay, so basically the surface here is aluminum. So for the recoating, we need to remove this very thin layer of aluminum, and we need to put another one. So the new layer, the new aluminum layer, means that the mirror will look like a new mirror. So basically, after a few days, maybe 3 4 days, when the mirror is ready with the new aluminum layer, we need to put the mirror again in the vehicle. We need to transfer the mirror again to the telescope platform. We need to insert the mirror inside of the main enclosure, and we need to install the mirror again here. So after that, the telescope and the mirror will be ready again for observations, and the mirror, as I told you already, will look like a new mirror. So that's the information regarding maintenance.
Thanks for it. And here Ismail mentioned that he had the chance to see part of this procedure one time, and it was very impressive, he mentions. Okay, how about another question? Yesterday, a bit after midnight, there was an 6.4 earthquake in Santiago, which is not big for Chilean standards, but what's happened with our earthquakes near the observatory?
This observatory, in the same way like any building in Chile is built, we have some protections against the earthquakes because Chile is a seismic country and we have some earthquakes sometimes. So in this case, we have some protections in the underground of this platform, acting like a cushion to protect the main facilities. And we can say, in theory, we can be okay even with an earthquake of 8 magnitude with epicenter in Antofagasta. So as you can see, it's pretty strong. So far, during all these years, more than 20 years, we haven't had a serious issue with an earthquake because we have been able to handle this situation, and the engineers are prepared to fix and take a look at any problem in case we have a problem with an earthquake. But in general terms, the observatory is pretty strong regarding that because well, Chile, as I told you already, is a seismic country, and we have to pay some attention to this kind of protections when we have this kind of seismic activity.
Yeah, and I guess, well, you always need to do some recalibrations after a seismic event. Okay, we have a question here before we continue. What is about the estimated value of these equipments? Do you have any number in your head?
Not for one single mirror, um, but I think that um, it was something like a little bit more than 300 million euros or something like that. But you need to remember, well, this is some more roughly about $500 million, but you need to remember that this is 20 years ago. So you need to consider that 20 years ago, um that amount of money is not the same like today. So because of inflation and so on, but it was roughly 300 million euros or $500 million, something like that. But I'm talking about the general project of the VLT.
Yeah, so that would include like building the roads, the flattening the top of the mountain, and everything, right?
Sorry, say again.
That would include like flattening the top of the mountain, building the road all the way to the summit, building the facilities, not just the telescopes in itself.
Yeah, exactly. Yeah, I mean all the cost involved in all the project, including all the necessary actions, activities such as to flatten the mountain and so on. Yes, it's not only the telescopes. Yes.
All right, thanks. Well, I guess we can continue, and I remind everybody that if you have any more questions and doubts, you can always leave them in the chat, and we'll have a second round to answer any inquiry that you have.
Okay, thank you, Hector. So we are going to continue, and as I told you already, we are going to continue with the control building. So in this case, here we have the control building. This is the view from the opposite side of the control building, and we are going to take a closer look. And we are going to this place in the last floor of the control building, and here we are. Well, as you can see, we have several separated workstations. For example, this one. Okay, we have workstations for each telescope. So in this case, this is the workstation for UT3 Melipal, and you can see that we have several computers. We have some people working here, but basically all operations with Melipal are from here. Okay. In the opposite side, we have the workstation for another telescope. We have the workstation for the UT4 Jepun. So all operations with Jepun are from here. So we have again some people working in the workstation, and that they are working specifically on this telescope. Now, if we continue in this virtual corridor, we can see the additional workstations for UT1, 4 and 2, as you can see here. We have again several terminals, computers. We have some people working, but all operations with UT1 are from here. And in the opposite side, we have the workstation for the last big telescope, Kuyen, or UT2. Okay, so in this case, we can take a closer look to this one. We can access the workstation here. So just to give you a general overview, um, all the telescopes, instruments, and systems explained before are controlled from here, from the control room. So during the day, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. And each night, we have a telescope operator and an astronomer per telescope. So in this case, this person is the telescope operator, and let's suppose that this person here is the astronomer. So the telescope operator is the person in charge of the technical details and the movement of the telescope. So basically, this person is like the pilot of the machine. And the ESO astronomer, in this case, is in charge to direct the scientific observations and will decide the next steps. So basically, is someone like the co-pilot. Okay. Now, the observations are performed by experts from ESO for scientists from all the planet. Okay, so this is what happens here. This is what happens in the control room. As you can see, it's not too eccentric. It's just an office space. Um, and we have people working here all night, of course, from sunset to dawn, because we need to take advantage of all the night. Okay, because this is the most important resource in an optical observatory. Okay, so this is the main information here in the control room. So now we are going to come back to the main platform. Okay, and now, well, right now you have a lot more information about the observatory and the people working here. So now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean, La Silla, Paranal, and Chagnantor. So scientific staff from different countries are using the ESO telescopes to study objects near to our home, the solar system, and also others located in the more distant places in our universe. So right now we have a video to explain that. So please, Hector, we can show this video to our virtual viewers.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, well, this was the top 10, but we have something else. We have just one more thing. We have some special news regarding a black hole. So, Hector, do we have this additional news? Okay, so basically this was a very important news from some years ago now. Well, a team of astronomers was able to capture the first image for the first picture of a black hole. The Event Horizon Telescope, or EHT, is acronym, an array of 8 ground-based telescopes distributed on the planet. They were working as an international collaboration, and they were able to achieve the first direct evidence of a supermassive black hole. This picture reveals the black hole in the center of the Messier 87. This is a massive galaxy in a close galaxy cluster in the Virgo constellation. This object is located 55 million light years from Earth, and its mass is about 6,500 million times the mass of our Sun. Okay, so we hope you liked the top 10. This was only a fraction of the discoveries, thanks to the ESO telescopes and the scientific staff behind them. Okay, so now we can continue. And from the platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. As you can see, the sky is almost completely dark with the last traces of light from the twilight, and the moon is below the horizon and the sky is full of stars. So here, in first place, we can see a very popular constellation just above the Antu telescope, the first one in the picture. So this one is the Antu, sorry, this is the Orion constellation. So I am going to do a close up. So basically, this one is a very popular constellation. In the mythology, it represents a hunter. So you can recognize this constellation because of the three stars here, because they are somewhat aligned, representing Orion's belt. And inside of Orion, we have another interesting object. We have the Great Orion's Nebula right here with this pink tone. So this is Orion. It's visible from the northern and southern hemispheres. So we can see this constellation from any place. But now we are going to change the position in the sky, and we are going to move to the brightest star in the night sky, this one. This star is called Sirius, and this star belongs to the Canis Major constellation, representing Orion's hunting dog. So in this case, this star belongs to a constellation that in the mythology is related to Orion, because Orion has two hunting dogs, and in this case, the Canis Major is one of them. Okay, so that's why it's so interesting to know this story in terms of mythology. Now, if we go a little bit down, next to Antu, the telescope here, we have another important object. We can see that here we have um, an open cluster. This open star cluster is called Pleiades, okay? And this is located in the Taurus constellation, okay? So the majority of those objects are visually close to a specific area, a very populated area with a lot of stars. I mean, this one. Do you see? This area has much more stars if you compare with this area or this area. So actually, when we are looking at this band of stars, we are looking at one of the Milky Way arms, our galaxy. And our sun is only one among hundreds of millions of stars. So during the winter in the southern hemisphere, we can see the center of the Milky Way, and this is another area full of stars between Scorpius and Sagittarius constellations. And you can see all this area from this hemisphere, from the southern hemisphere. Okay, so now we are going to move to another sector in the sky to find two spots. We are going to change the direction, and we are going to center the view here. Okay, so what is this? These spots right here are the Magellanic Clouds. So we can see here, up there, the large Magellanic Cloud, and down there we have the small Magellanic Cloud. They are not actually clouds, of course. They are galaxies with an irregular shape. Both of them are visible to the naked eye, in a clear night like this one. So this name refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people were totally unaware about what a galaxy is. Okay? Now, another important area here is the smallest constellation in the sky. I mean the Southern Cross, this one. So we can take a look here and we can explore the shape of this constellation. In this case, the Southern Cross is like a little bit tilt. It's not upright, but it's fine. This is an easy constellation to find in the sky, only visible in this hemisphere, and a good guide to find the South Celestial Pole, a projection of the Earth's South Pole. So during the night, the stars appear to revolve around this point, the South Celestial Pole. So to find this point, we have to do something. Basically, we have to use the Southern Cross to find the South Celestial Pole. So in this case, we have to project 4 times and a half the longer stick of the Southern Cross. I mean this one. So if we do that, we can project 1, 2, 3, 4.5, and more or less like here, we will have the South Celestial Pole. Okay, so basically, if you look at the horizon, if you look this to this point, but now if you look to the horizon just exactly here at this position, you will look at the south cardinal point. So basically, this is a very important reference in case you are, I don't know, lost in an isolated place like this one, because you can find the south cardinal point when you are looking to this toward this direction. Okay, so this is the conclusion of our visit to Cerro Paranal, to the mountaintop. So now we are coming back to the platform in the daytime. So we are going to return and we are going to change the view for daytime. And now the last part of this virtual visit will be in the base camp. So we are going down to 2,400 meters in order to visit a very special oasis. So for this purpose, we have to rotate the view and we have to search for the base camp of Paranal, this one. So we have to go to this place, to the base camp. This is something like a mini city because we have all the facilities here for the people working in the observatory. So we have some rooms for contractors, a warehouse, the mirror maintenance building, a gym. So basically, we have a lot of things. But the place I want to show you in this case is the residence. The residence of Paranal. This is a place where the ESO staff can stay and rest. So the residence is here. So we are going to take a look to this place because the residence is the home of the ESO staff during the work in the desert. And you can see that this very special place, it has this kind of, let's say, dome. And it looks like an underground place, but it's actually the shape of the land. So only this entrance, for this entrance, you need to use this kind of ramp. But in the opposite side is like a regular building with with a regular wall and many windows. So we are going to enter now to the residence to take a closer look. Okay, here we are. So basically, here the workers can enjoy a more humid air, and as you can see, we have a swimming pool, green areas, and also some rest if you compare with the desert and the intense sunlight from the outside. So we can see here that we have a lot of interesting things. Of course, we have the swimming pool, we have some nature. From this perspective, you can also take a look at, this is the restaurant over there. This is the lobby, this is the reception. So it's basically very similar to a hotel, but in this case, it's only for the staff. So it's not for regular visitors or tourists. This residence has 108 rooms. Most of the rooms are located inside. If you pass through this area, you will find the rooms. We have 108 rooms, and this is, as I told you already, for the staff. I mean, for the people with a contract with ESO, or uh, or the engineers and scientists coming from other countries sometimes. Okay, so this is the last part of this visit. So during this time at the residence, I would like to know if maybe, Hector, do we have any additional question before we continue this tour?
Okay, we have a question about a guaranteed time for Chilean astronomers. Can you tell us about that?
Yeah, I think it's important to distinguish the difference because we can say usually that we have an allocated time. It's usually up to 10%, but it's better not to talk about specific numbers because it could be sometimes less than that. It depends on many factors. But it's important to distinguish the notion that this allocated time is not for Chilean astronomers, it's for Chilean institutions, such as the Universidad de Chile, Universidad Católica, and I mean the departments of astronomy. So because when you have a Chilean institution, in a Chilean institution, you can have maybe a Chilean astronomer, but also maybe you can find a French astronomer, and an American astronomer, and a Danish astronomer. But the important thing is let's say, the nationality of the institution, not the nationality of the astronomer. So basically, is let's say up to 10%, but it's better not to talk about the specific numbers. But it's a important warranty time.
Okay, that was the last question that we have. So,
Uh-huh.
if we doesn't have anything else, I think is we are in good time to end the tour. So, for my part, I say goodbye to everybody watching, and reminded that we do these kinds of tours every Saturday, for Paranal Observatory and the Sea Observatory, English and Spanish. So keep an eye on our social networks to know when the next tour is and of which place and in English language. So yeah,
Okay, thank you very much. Thank you, Hector. We remind you that all these visits, information, and pictures are available on the ESO website. And and also we have a survey to receive your comments about this tour. So in case you want to leave your comments or questions, so the link to this survey is on the chat of the streaming. And well, in this way, we finish our tour today. I hope you like this virtual experience. Please stay alert to the ESO social networks to know when we will have the next tour. Okay. So on behalf of
yeah, and
ESO, I want to say thank you very much for your presence.
yeah, maybe one last thing before we go. Remind people that there is also in-person tours of the observatories that are free. You just need to sign up in a website, and they're every Saturday for Paranal, one at 10 a.m. and one at 2 p.m. And for Lucia,
Exactly.
yeah, as well.
Exactly.
All right, so
Okay. Thank you. Thank you very much. Thank you. Bye bye.
bye.